Good morning, children. And today we will be studying the nucleophilic addition reactions of the carbonyl compounds. Now, this is basically shown by aldehydes and ketones. Aldehydes show it much easily as compared to the ketones because of the steric hindrance that is seen in the case of ketones due to the bulky alkyl groups around the carbonyl group. So we'll first start with what exactly is a carbonyl group, and then from there we'll proceed on to study about the addition reactions. Okay, so let's go to that, and we'll start off saying that in the case of aldehydes and ketones, which have a carbonyl group, okay, the carbonyl group is represented as C double bond O. All right. If you look at the compound, del oxygen is del negative, carbon is del positive. Again, if both of these valencies, if this is going to have an H, let me show it separately, H and an H and a C double bond O, this is an aldehyde. This is called as formaldehyde, methanal. So the name of this compound is methanal. However, if you have one of the groups replaced by a CH3, all right, and you have a C and an H and a double bond O, then this becomes an aldehyde. In fact, the CH3 can be any R, and this is going to become an aldehyde class of compounds. All right, aldehydes. On the other hand, if both of these get replaced by a CH3 and a CH3, such that you get C double bond O, then these kinds of compounds are called as ketones. This particular compound is acetone. This particular compound is acetone. Okay, or you can also call it, according to the IUPAC name, it's going to be propanone. However, these alkyl groups can be same on both sides. They can be different on both sides. It's not necessary that they have to be methyl groups. They can be ethyl groups. They can be propyl groups, whatever. But we are basically interested in this part of the compound, which is the carbonyl group. Okay, now why are we interested in this is because you see, due to the doubly bonded oxygen, the carbon is kind of getting a partial positive charge and oxygen develops a partial negative charge, which makes the carbonyl group very susceptible to nucleophilic additions. Okay, now what is a nucleophile? A nucleophile is one which is, all right, rich in electron, and it is going to attack a positive center. So these kinds of compounds show, or the carbonyl groups show, nucleophilic addition reactions, or they can also be, nucleophilic additions followed by a loss of water molecule, or they can just simply add up. When there is a simple addition, then you have to know that the why does that simple addition actually occur. The reason being that if I go to this compound again, you will see that in this case, if I study the structure of it, then since C is doubly bonded to oxygen, and in this case, all right, C is doubly bonded to oxygen, the structure of this compound is such that you have a sigma bond, sorry, you have a sigma bond and a pi bond. Okay, and the bond angles between the two hybrid orbitals is going to be 120 degree, because each carbon atom is sp2 hybridized. This carbon atom is sp2 hybridized. Okay, all right. When the addition occurs, then this carbonyl group is ready, the sigma bond remaining intact, the pi bond is going to open up, and the carbon is going to attain a tetrahedral structure. That is, the hybridization changes to sp3. Okay. Now, when the hybridization changes to sp3, then in that case, what is happening is that the geometry of the molecule is also changing. it is changing from an sp2 hybridized carbon planar structure to a tetrahedral structure. So this is an sp3 hybridized carbon atom that we get. Now, does this mean that even compounds like acetic acid are carbonyl compounds? No, because very often children ask that, Miss, will this also be a a carbonyl compound because it has a CO group here? No. Actually, in the case of carboxylic acids, what happens is that the hydrogen is lost as an H plus very easily, and it is the carboxylate ion which actually functions together, and therefore they don't fall under the category of carbonyl compounds. They are carboxylic groups, and if the OH is replaced by some other group, like for example, if you have a compound like CH3, C double bond O and a Cl, then this is acetyl chloride, but it is not a carbonyl group because the derivative, that is the acetyl chloride, has been obtained from the carboxylic acid group. All right. So this is about the compound which are called as carbonyl compounds. Aldehydes and ketones will fall under this category of compounds. So we are basically doing the nucleophilic addition reactions. Okay. So let's go to what are the compounds that we will discuss under the nucleophilic addition to show. So the ones that you have to do is the reaction with HCN and the reaction with NaHSO3. Both the compounds have their own importance when they show addition reactions. Actually, if you see in the case of HCN, HCN is positive, that is hydrogen cyanide is positive, and H and Cn negative. So when this adds up to a carbonyl group, that is C double bond O, okay, then in this case you can see what is happening is that the H plus is going to go with the oxygen. These electrons of the pi bond will move to this oxygen, and therefore what you are going to get is a C, and this O, which has now got a negative charge, will accept a hydrogen, and this one is going to change into addition of a CN. Such compounds are called as addition compounds, are called as cyanohydrins. They add up, and these are called as cyanohydrins. Okay. Now, what is the importance of this reaction? The importance of this reaction is that you can actually add a carbon to the carbon of the carbonyl group. You see, why are these reactions called as nucleophilic additions? Because it is the nucleophile that attacks the carbon skeleton, or the partially positive carbon atom of the carbonyl group. Hence, the name of the reactions are nucleophilic addition reactions. Okay, if the electrophile was to attack the carbon, then you would call it as electrophilic addition. You know that the reaction mechanisms are named whether the electrophile or the nucleophile is attacking, or whether it is an addition or a elimination or a substitution reaction occurring. So in this case, it is a nucleophilic addition because a nucleophile attacks the del positive carbon, that is partially positive carbon of the carbonyl group. Now, the second reaction that you have to do, this is the first reaction. The second reaction that you have to do in this case is with NaHSO3. Now, what is this reaction about? The carbonyl group C double bond O, all right, this is the carbonyl group, is supposed to react with NaHSO3, sodium bisulfite compound. Okay, when it reacts with this, it is going to show an addition, just like we saw in the case of HCN, and it is actually going to show a two-step mechanism, and you are going to get C, because in case of NaHSO3, it is the Na plus that will be obtained. All right, and this is HSO3 minus. So it is the O negative Na plus, and here you get the SO3H. SO3H. After this, immediately there is going to be a proton transfer and a kind of a rearrangement, you can say. The proton transfer occurs, and this compound changes into COH and SO3Na. SO3Na. Okay. So this is what you will get here. Now you remember these compounds, this reaction is important because these addition compounds that are formed from the carbonyl compounds, they are white crystalline in nature, they precipitate. They can actually be used, for separating the aldehydes and the ketone compounds from other, like you have other a mixture of compounds, then you treat them with the sodium bisulfite compound. It is going to form an addition product, and the addition product that is going to be obtained is going to be it's going to be crystalline in nature, and it can be crystallized out. And therefore after that you subject it to hydrolysis in presence of a acid. It will give back the original aldehyde or the ketone. Again, keep in mind that these reactions are easily shown by the aldehydes and methyl ketones, but the bulky groups, they usually do not show this kind of a reaction. Now in the lab also you will have to do this reaction for acetone, because acetone you have to do in the lab in the organic compound practicals, and there also you will be able to see the crystals forming very, like, it's quite obvious the reaction can be seen. The next set of addition reactions are with ammonia and ammonia derivatives. Okay, so these are again important with ammonia. Now, why did I not write ammonia with those two compounds? Is because when the reaction is with ammonia, it is an addition reaction undoubtedly, but with ammonia derivatives, it is followed by a loss of water molecule. It is followed by a loss of water molecule, and therefore you have it written differently. However, with ammonia, let us see what happens. C double bond O, this is made to react with ammonia, so I can write HNH2, and it's going to add up to form aldehyde ammonias. So here there is basically no loss of water molecule, but an aldehyde ammonia is obtained. Formaldehyde is the only aldehyde which reacts very differently with ammonia, and it goes on to form the other products. Okay. However, it is the rest of the aldehydes containing this carbonyl group, they undergo this reaction very easily. All right. Now, will ketones also show the similar reactions? Yes, it also shows. But again, as the alkyl groups become bulkier, steric hindrance becomes more and more, and therefore the reaction becomes difficult with the case of higher ketones. Now, we said that formaldehydes behave differently with the addition of ammonia. Yes, it does behave differently, and it gives a compound which is called as urotropin. Okay, it forms an kind of a polymerized compound, or you can say addition reactions occur, and such that it forms a compound which is called as urotropin. Now, the details of which maybe we'll discuss in the other video. Okay. Now, coming next to the reactions with ammonia derivatives. So first we must understand what are ammonia derivatives. If you look at ammonia molecule, like I have written here, you can also write it here, NH2, okay, and put a Z here. This Z stands for any derivative that can be there. Okay, so if this Z is any other group that is attached to ammonia, then it becomes ammonia derivative. Now, what kind of groups can the Z be? All right, it can be, Z can be a CH3, okay, it can be an NH2, all right, it can be an NH2, okay, it can be an, in this case, we can also have a OH group, okay, it can also be NHC6H5, okay, it can also be NH, and then the phenyl ring that is there is having two second and the fourth position as NO2. So this is called as 2NO2, okay, 2,4-dinitrophenylhydrazine. All right, and you can also have uh, a semi-carbazide that is, that Z can be NHCONH2. Mind you, in all these compounds, the Z has been replaced by these groups. All these groups have a definite name to themselves, and once it is formed, the compounds related to this will be formed by the mechanism that we are just about to discuss. All right. Now, what kind of a nucleophilic addition reactions followed by loss of water molecules will occur in these compounds? To understand that, first let us do the mechanism. Now, in the case of a mechanism, the first step of the nucleophilic addition of ammonia derivatives is the first step is the nucleophilic attack. The first step is the nucleophilic attack. So the nucleophile first attacks. Okay, nucleophilic attack is the first ATACK attack. All right, now which one is the nucleophile and what is going to happen if you look at the molecule closely? This is the carbonyl group. Okay, and it is about to react with a ammonia derivative. Ammonia derivative, if you look at it, it is N, okay, H2, and if it is N, H2 and the Z, it is which is having, a lone pair of electron. This is the one which is carbonyl carbon. Okay, and then this is del negative, this is del positive. So in the next step, what is happening is, since the nucleophile has attacked, you're getting a all right. In this case, these will remain as it is since the nucleus negative. All right, proton transfer. All right, from where will the proton transfer? Now, if you look at the molecule, you will see that in this case here, this is negative. This hydrogen is, actually more valency than it should show. So one of these hydrogens from here is going to get here and NH, Z, and you're going to get an OH. Okay, so this is the compound that you are going to get. In the next step, there is going to be protonation. Now, after the proton transfer, since the reaction is going to be carried out in a weakly acidic medium, because it is necessary that the pH be maintained between 3 and 5, then what will happen is that the protonation of this group is going to take place. So the protonation of this group will take place and it will result in the formation of a C, okay, and you get an N, H, Z, and here it is going to be O, H, and then H, and this is supposed to come here so that the water molecule can be given out, and this is what is happening here. Now, in this case, when this water molecule is given out, when the water molecule is given out, the next step that happens is, see, after the proton transfer, the next step was, if this was the first step, this is the second step. The third step was the protonation of the OH group, okay, which we have shown already in the above reaction, in the above presentation. The fourth step that is involved is that a deprotonation occurs. Deprotonation occurs. Deprotonation of what? The deprotonation is shown like this. See, this is going to have a double bond with nitrogen. The Z will remain, and this bond which has been, lost here, this carbon oxygen bond which actually ruptured here will allow the bond to form a double bond with nitrogen, and the addition part of the compound, the derivative part of the ammonia molecule remains as it is. All right, so these are the four basic steps that are involved in the you can say the mechanism that is involved in the nucleophilic addition. You see that a water molecule is lost. That is why we say that these examples are, this mechanism involves a loss of water molecule. Okay, now let us see how individually each one of them is going to add up and what is their name of the compounds that are obtained. Okay, so we'll go by that. The first compound that you can talk about, we saw in the group, was about CH3. So if the ammonia derivative is all right, okay. If I'll show the carbonyl group with C in red with C double bond O, okay, this is supposed to react with, okay, it's going to be an NH2, okay, and the addition, the derivative part I can show in blue, that is, let us say it is CH3. Now this is a primary amine. This compound is actually a primary amine, okay, amine. When this undergoes that same mechanism, the compound that we are going to get is a C, all right, and in this case, one second. In this case, then you are going to get a doubly bonded nitrogen and the CH3 remains as it is. Mine is obtained. Now, if you have noticed that, if you will notice rather, you will see that every time the addition happens, it is the 2 hydrogen of the nitrogen molecule atom that is lost, and the oxygen of the carbonyl group is lost, and therefore a removal of water molecule can be shown in general, and the derivative part of the ammonia molecule remains as intact. Okay. Now this compound, you are starting with an ammonia derivative that is an primary amine, and therefore what you are getting, the name of the compound is imine. All right. This is the first one, let us say. Now let's go to the second one. This is the first one. Let's go to the second one. Now, in the second one, again, we will take the carbonyl group. I'm going to represent it like this. It will occupy less space. And this is the carbonyl group. And we are going to react this with an ammonia derivative. All right. Well, let us say it is an OH group that is attached. All right. Listen carefully. The name of this compound is hydroxyl amine. All right, hydroxyl amine. If you actually know a little bit of nomenclature, you will be able to know why the name is like that. A hydroxy group has been attached to an NH2, so it becomes a hydroxyl amine. All right. And when a hydroxyl amine in a acidic, weakly acidic medium is taken, that means the pH is around 3 and 5, somewhere around pH equal to 5 is a better option, because see, if you take a stronger acid, the ammonia derivative, it will itself will react with the acid to form the salt, whereby which what will happen, the purpose of the reaction to occur is defeated. So when it happens like this, then the compound that you will get, it's a very simple thing to remember. Just keep adding the N, and this is going to be the OH. If you notice, look at it carefully, the hydrogen and the oxygen, if I show it in yellow, it is this and these that are actually lost after the total mechanism occurs, and carbon gets doubly bonded to nitrogen. Okay, and so that is how you are going to get the compound. Now, what is the name of this compound? These compounds are called as oximes. These are called as oximes. All right. So you get an, suppose if it is an acetaldehyde group, obviously one of this is going to have a CH3 group, then it is going to become an ethanal oxime. Ethanal oxime. Always in all these cases, there is a removal of water molecule. So I can show it on the arrow here. I can show it here also. Okay. Then comes the third one, the third ammonia derivative. In the case of the third ammonia derivative, this is C double bond O. We are going to take it as NH2. Okay, and one of the hydrogens has been replaced by another NH2 group. So you get it as this one I can write in blue. So this is going to be NH2. All right. This is all representing the blue color is representing the Z that should be there in the derivative. This compound is called as hydrazine. This is called as hydrazine. All right. And again, when it reacts in the weakly acidic medium, you're getting H plus minus H2O. Then in this case, it's going to convert into, I have to show this in red. So it's going to be like this and double bond N. Okay. And the attachment will be shown like this. NH2. All right. So what is the compound formed? These are called as hydrazones. These are called as hydrazones. hydrazones. All right. Next, fourth one. Let us see what is there in the fourth one. In the fourth one, we are going to use C double bond O group plus NH2. All right. And in the attachment, that NH2, one of the hydrogens of the NH2. See, this is actually going to be like this H, and another H would come here in this place. But what we will do is, instead of that, we are going to write a C6H5. C6H5, again, the reaction conditions being the same, loss of water molecule occurring. This compound is called as phenylhydrazine. All right, the name of this compound is phenylhydrazine. Phenylhydrazine. All right, why is it phenylhydrazine? You see, as a phenyl group has been added to the hydrazine, so it becomes a phenylhydrazine. And of course, the compound obtained in this case is also going to be like that, C double bond, then N. All right, the attachment we will show as NHC6H5. So this is phenylhydrazone. The compound obtained is phenylhydrazone. Okay, now the next one that we will do in this case. The next one that we will do in this case is of, that was, I think, the fifth one we did. Just let me check. That was the fourth. So we have to do the fifth one. So in the fifth one, again, carbonyl group is taken, C double bond O. This is made to react with NH2, and the Z that we are taking, N, okay, H, all right, is a 2,4-dinitrophenylhydrazine. This is NO2. This is also called as DNP in short, dinitrophenylhydrazine. Now this is an attachment. Now what you do is, when this is again under the reaction conditions of H plus and losing a water molecule, see children, however big be the molecule, the ZB, however big, the reaction is between, as I told you earlier also, it's between this and this being lost. Okay, so in this case, what will be the compound that will be obtained? I'm going to show it here. It's going to be C, all right, then double bond N, okay, then the attachment, that is N, H, all right. This is the phenyl group that we are showing. It remains as it is, and you get a 2,4-dinitrophenylhydrazone. You get a 2,4-dinitrophenylhydrazone. So this is, name of this compound is 2,4-dinitro. I'll continue down here, phenylhydrazine. Also called as DNP. All right, but this is going to become the hydrazone. After the reaction, it becomes hydrazone. Now, probably the last one that we have to do is with semicarbazide. Now, in this case, again, we'll take C double bond O plus NH2, okay, and then the attachment that in place of Z you have is, and N, H, C double bond O, and then NH2. You see, actually a urea molecule is getting added up here. Urea is NH2, CONH2. This part of the molecule, actually, if you look at this, one second, if you look at this, if there was a 2 here, in this case, it would be a urea. So this part is adding up in place of the Z, that is ammonia derivative, and this compound is called as semi-carbazide. Semi-carbazide. All right. Now, if you look at it, it is semi-carbazide, fine. But if you look at it, the urea part has just been added to the NH2 group. And when this reacts, actually in again H plus and minus H2O, you will get what is the compound is going to be like C double bond N, Okay, that C double bond N bond is established in all the compounds. All right, and H2 has been lost, and so then you will have an N. All right, then H, and of course the phenyl ring with the nitro groups. So you can show the nitro groups here as NO2 and here as NO2. So carbazone, semi carbazone. All right, so suppose if the group, this is the semi carbazone, suppose let us take one more example here and make this H. All right, H and H here, then this is going to undergo the reaction, and the compound, if this was a formaldehyde that we took, obviously this is the compound that you will get, then this is called as methanal semi-carbazone. Name of the compound will be methanal semi-carbazone. Why? Because this part of the molecule is the methanal part, and of course the semi-carbazone. Similarly, depending upon which group has been attached, it can be named according to that. All right. So this is about the ammonia derivatives. All right. In this case, you find that the addition compound which is being formed is actually losing a water molecule and yielding a compound which is containing a carbon nitrogen double bond. All right. Now, what is the importance of the pH when this reaction is supposed to take place? When these reactions of the ammonia derivatives is supposed to take place, then the pH has to be, well maintained between 3 and 5. Because if the pH is not properly maintained, and if the pH is, very low, what are the consequences? Let us see. If the pH of this reaction, if the pH is, very low, what will happen? That means pH being very low means it's highly acidic. And when it is highly acidic, the NH2 group is only going to react with the H plus to form the corresponding salt. Suppose it is HCl, it will go on to form the chloride salt. All right, that is why the pH has to be, should not be very low. All right. On the other hand, if the pH is very high, then the protonation of the OH group will not occur. So what happens if the pH is very low? pH is very high. That means it's going to be an alkaline medium. And in the alkaline medium, the step where the protonation has to occur for the removal of the water molecule, which is the main step, that only will not happen. That is, if we are taking C, all right, let us say the N H2 Z has occurred, and this is O negative, then there is a proton transfer, and what you are getting is a C and an NH dot, the the derivative that is there, and this is the OH. After this, it is necessary that the protonation of this occurs. From where will the protonation occur? H from the nitrogen is not easily available. So it is the H plus that is going to actually attack the oxygen. And therefore, in the next step, then the water molecule will be given out. So for this step to occur, the nature of the solvent or the medium should be slightly acidic. As we said, if it is highly acidic, then it will not occur. The protonation will, if it is highly acidic, then the ammonia derivative itself will undergo the reaction. Okay, so this was about reactions of ammonia and ammonia derivative, that is nucleophilic addition reactions of ammonia derivatives. What are the other reactions that we have to study under this? Under this, we also have to do the addition of the Grignard's reagent, all right, which is simply an addition to form the different kinds of alcohols, which we have already discussed in the previous class. Like formaldehyde is the only aldehyde which will give you a primary alcohol. The rest of them are going to give you the secondary alcohol, and ketones are going to give you the tertiary alcohol. And one more, the next one that you have to do, a very important reaction in this case, is that of aldol condensation. All right, now let us see. For aldol condensation also in details, I have already prepared one video for you to see. But however, I'll just discuss the aldol condensation here also. Now, in the case of aldol condensation, what happens is that, as the name suggests, it is a condensation of the two molecules of aldehydes and ketones to form larger compounds. All right. In this case also, it is the nucleophilic addition. There is a loss of water molecule, and in this case also the condensation reaction is favored by the aldehydes. Ketones have steric hindrance. But one important thing that we have to know in aldol condensation is the acidity of the alpha hydrogen atom, okay, which is very important. See, in this case, if this is one of the carbonyl groups, this is going to react with another carbonyl group, all right. This is supposed to react with another carbonyl group, okay, and condensation will occur in such a manner that one of this, if this is the attacking reagent, all right, let me show it with acetaldehyde so that you can understand. Now see, both the compounds are of the same compound, all right, they are molecules of the same compound, but I'm showing the two differently such that when the addition is occurring and the condensation takes place, what is the product formed and what is the important thing to note in this case. Now, this proceeds in an alkaline medium. This is a base catalyzed reaction and it proceeds in an alkaline medium. When it proceeds in an alkaline medium, what does this OH minus do? It actually abstracts an alpha hydrogen atom. So let us say that the blue molecule is the attacking reagent. This is going to generate the nucleophile, or this is going to form the nucleophile. So how will that happen? If I talk about this part, then let me just show this in yellow. You will see that this is H, okay, C, this is CH3, all right. And of course, you have a doubly bonded oxygen. Now, this carbon is called, referred to as the alpha carbon. Carbon next to the carbonyl group is referred to as the alpha carbon. And this has the hydrogens in it. Now, when this has hydrogens in it, OH minus is going to attack one of these hydrogens, any one, okay, and it's going to form H2O. When it forms an H2O, it has to abstract this hydrogen from this carbon as a positive ion, and therefore what you will get is actually an H, C, double bond O, and a CH2, all right, with a negative charge. All right, it is this is the attacking reagent. This is the main nucleophile that is going to attack the molecule. All right, so this is going to, the one in blue is going to behave like what I have shown in yellow. This blue molecule is actually going to form a nucleophile which is going to be like this. So now let us see what happens in the next step. So I'll go to the next page, and if I am showing, let me do an acetaldehyde, let C double bond O, and you have an H, and the one in blue we said has formed the nucleophile. So it is going to attack through the CH2 side. So the CH2 with the negative charge is going to attack the molecule. All right, here. Why will it attack? Because you know that this is del positive and this is del negative. So when it attacks, it's going to form an addition compound, which is going to look like CH3, C, all right, and this H remains as it is, and this oxygen here, these electrons will move to this oxygen. So this is going to get a negative charge. Okay, this is not writing correctly. Let me just erase this and do it again. This is negative, and here it is going to attack. The CH2 is going to attach itself. All right, CH2, C double bond O, and then H. All right, then this is going to actually pick up an H plus from the solvent, and then it is going to convert into the molecule which is going to look like this. That is a CH3, all right, a COH, all right, after it has picked up an H plus. This H I'm going to show here, and the addition compound is going to be CH2, okay, C double bond O, and then H. So what is important to note here is that this compound has been formed from two molecules of acetaldehyde. And if you look at the molecule here, you will see that it is a condensation product that has been obtained. Of course, after this, what will happen is that the molecule can readily give up a water molecule. And when it gives up a water molecule from the alpha beta position, this happens, very easily. And therefore, sorry, this is alpha and this is supposed to be the beta carbon. All right. So alpha beta position, and then it gives a compound, an alpha beta unsaturated compound is obtained. All right, so what you get is actually a CH3. This is also called as cinnamaldehyde. H double bond, all right, then CH and a CHO. Now this is the blue part, okay, which has been obtained. Now this compound in particular is called as an aldol because it has an aldehyde group and it has an alcoholic group. One point to note here is that the attacking reagent retains the aldehyde group. The substrate molecule, which what is the substrate molecule? The molecule on which the nucleophile is attacking. So the substrate molecule will lose its aldehyde group and convert into an alcohol, whereas the attacking reagent is going to retain its aldehyde group. Okay. Now this kind of aldol condensation can be carried out between two different aldehydes. It can be carried out between an aldehyde and a ketone. But one thing is for sure that is required is that the one of the reagents, I mean, one of the molecules taking part in the aldol condensation must have an alpha hydrogen atom. Okay. If the alpha hydrogen atom is not there, generation of the nucleophile will not occur. And that is why we know that, the benzaldehyde and formaldehyde, they do not undergo aldol condensation. Ketones also undergo the same mechanism, but with difficulty because of the steric hindrance and the bulkiness of the group. But otherwise, the reaction is easily shown by the aldehydes. In fact, if the compound has more number of alpha, it has acidic hydrogens at the alpha position. Like in this case, I'm marking that in yellow. If you look at these two are also alpha hydrogens. They also can, undergo repeated aldol condensation by forming the nucleophile again and attacking the molecule, whereby which any compound which is having an aldehyde group, all right, can undergo repeated aldol condensation and result in the formation of a resinous mass. Okay, that is, it will have more thick nature and it forms a resinous mass, so that repeated aldol condensation may also occur. All right, this is one part that you have to know. And of course, what are the products formed when you take different kinds of aldehydes? That part also I'll show you. Suppose you have H, C, H double bond O. Now this is a formaldehyde. Now two formaldehyde molecules, if they are involved, they undergo Cannizzaro reaction, which again I have discussed in the other video. But if in this case, if I'm going to talk about a compound with a CH3, all right, if I'm talking about CH3, C double bond O and an H, okay, then here there is no choice. This molecule only will have to form the nucleophile, and this will always behave as the substrate molecule. So this will always be the substrate, and this one will be, this can form the nucleophile. You can see in this case also that if you look at the product that will be obtained, obviously in the place of, in the alkaline medium, the product obtained is going to be H, all right, then this is going to be the OH that will be attached, and here it is going to be the CH2, all right, C double bond O and an H. So in this case, you see always the hydroxy group is at the beta position. So in general, the beta hydroxy compounds are obtained. Beta hydroxy aldehydes are obtained. So the product of aldol condensations are beta hydroxy aldehydes, or sorry, beta hydroxy, yes, aldehydes will be obtained. All right, and then they very easily undergo alpha beta dehydration and result in the formation of compounds which are having unsaturation at the alpha beta position. Now if I'm talking about this same compound, then I can show you that this is going to form the dehydrated product as this, and then you will have a C, H and a CHO. All right, you give the IUPAC names to these compounds, they will always have the, in these compounds, the hydroxy position will always be 3 hydroxy butanal, 3 hydroxy pentanal, depending upon what kind of aldehydes or ketones we are taking into consideration. The last point that we can discuss here is that if the two compounds that we are taking for aldol condensation, both of them are capable of forming the nucleophile, then how will the reaction occur? Okay, so the second one that I'm going to show you here is a C2H5. All right, okay, let me draw the open structure for this and write. So CH, okay, one second, what happened? All right, so this probably got erased out. One second. Okay, let me go back to that. Suppose if we have two compounds, one is CH3, all right, C double bond O and an H, and the other compound that we are going to talk about is a CH3, which is having 3 hydrogens here, 2 here, and C double bond O and an H. Remember, the ones that I'm going to mark in yellow are the ones which can be pulled out by the OH to form the nucleophile. So which are those ones? This one can be given out, this one can be given out, or one from here can be given out. Okay, so when the red, that is the red colored acetaldehyde molecule, loses a hydrogen, then it's going to form a nucleophile which is going to be like this, CHO. And when the blue colored one loses its molecule, then hydrogen, then it's going to form a CH minus CH3, and it's going to form a CHO. All right. Now in this case, let me remove that plus sign from in between. So this is going to form the two kinds of nucleophiles that are there. All right, so this is one nucleophile and this is the second nucleophile. So when you look at these two, you will see that actually 4 different products can be obtained. All right, so let me see how it can be there. You can have, if I write the products as A and B, let this be A. Products are, I have to show with condensation, and this is B. So I can have 4 different kinds of products. What is the first one that I can have? I can have an A, all right, I'm showing the substrate molecule in A, to which 1 is adding up, to which 1 is adding up. Okay, I can have the other molecule, I can have the other one, okay, where I can have A, all right, to which the second nucleophile is adding up. Okay, in all these cases, the name of the compounds will be different. I can have a third product, okay, where I can use a B, all right, to which 1 is adding up. To which 1 is adding up, okay. And I can have a fourth B, to which the second is adding up. Now, these are the electrophiles that I am representing here. Now, vividly, if you see and if you draw the structures, you will get the correct aldols in each case. One I will do for you in the example. Let us see, we'll do the second one. Okay, so what is the structure like in the second one? We said the substrate molecule is going to be CH3C, and this is going to form an OH, okay, to which this electrophile is adding up. So how will the electrophile add up? I'll write it in blue. It's going to be CH, and you will get a CH3, and this is going to be a CHO. So you see, this is the aldol that we are getting. Again, it is a 3-hydroxyaldehyde. All right, the name of the compound is going to be 2-methyl-3-hydroxy. Always that, methyl or the ethyl group, depending upon the acetaldehyde nature. The alkyl group will always be on the second carbon atom if you're going by the IUPAC nomenclature. So this is 1, this is 2, this is 3, and this is 4. So actually what you're going to get is 2-methyl-3-hydroxy-butanal. All right. Similarly, you add up, try doing this out, and you will see that it can be actually obtained. More than one product will be obtained if more. Why? Because the 2 aldehyde groups that we are taking are different, and both of them can form a nucleophile. The nucleophile can attack that same group from where it has generated, or it can attack the other aldehyde group from which the other nucleophile has been generated. So children, this is all about the nucleophilic addition reactions. All these aldols, beta hydroxy compounds, are capable of undergoing dehydration at the alpha beta position. So they can form that, and of course, the reaction is going to proceed in the nucleophilic addition manner. Now, if I look at it, we have done all this, and with this, I think I can end for the today's class based on the nucleophilic addition reactions of the aldehydes and ketones, that is the carbonyl group. Okay. All right. So that is it.